So this is video 4 in a series of videos to help you with engineering. So we are looking at electronic systems today. Really, this is under the whole category of systems, and it should help you with the elements of revision with some questions. So good luck and watch through some of these questions to see how close you are to your answer. So here are some of the diagrams and some of the elements that you're going to need to revise. I would like to thank Paul Braden for his revision resource that he made for this. I'm just turning this into a video so that some of my students that are better when they are listening or they're more visual learners, this might help them as they're working through their revision. So we're going to be discussing analog and digital signals, sensor inputs, and different devices that you may add into a circuit. And we're going to discuss where you might use some of these. So have a go at some of these questions and see how close you get to your answer. So our first two questions that we are going to have in electronic systems are state two advantages of using digital signals instead of analog, and also name an input sensor that can be used to detect light changes, so detect the light levels. So pause this, write down your answer, and see how close you get to this. So, two advantages of using digital signals instead of analog. Well, it should be noticed that analog signals are continuous. They change, they vary. Make sure you're clear that you understand that. The diagram on the left here shows that. The problem with using analog is that analog signals are susceptible to noise or interference. So we can actually get interference from other cables. If you do computer science, you will know this as one of the networking questions when we're thinking about cabling. Digital signals are sent as pulses of information, such as on or off, so ones and zeros, and they can carry more information per second. And they do tend to maintain their quality better, and they're used for information sharing, such as, MP3 files. Then the next question we have was name an input sensor that can be used to detect changes in light levels. Well, we would tend to use a light-dependent resistor for this, because these can detect the varying changes in light. And when they detect that light level, they will change it into a resistance. That resistance, as it decreases, all right, it will decrease when the brightness increases. So the brighter it is, that resistance will increase. They are cheap to buy and easy to come by, and you might often see these in solar lights in your garden. So when it gets lighter, the light goes off, but when it gets darker, the light will come on. This is all to do with the change in resistance. And you can see this plotted on the diagram here. Our next two questions are, give an example of a circuit that can be used to produce a time delay and describe how each logic gate work. Pause the video. You might want to draw out your logic gates and do a truth table to see how they come out. But pause the video and see how you get on. So here's an example of a circuit that might be used with to produce a time delay. So you can do this by using a 555 monostable circuit. For example, this example shown below is to help you, and it will work out about roughly 11 seconds when the switch is pressed. And we can change the length of time by changing the resistor at R2 and the C1 capacitor. Increasing either will increase the delay. It's not always 100% accurate, and there can be variations, but this is what the circuit looks like. Now what we have here on the right is your logic gates. The first one is an AND gate, and I usually help my students remember this because it looks like a D, and the last letter of that is a D. So you can see here with an AND gate, both must be true for the outcome to be true. So both switches need to be on in order for the output to be on. With an OR gate, only one needs to be on. So it could be a 1 or a 0, or 0 or 1, or both could be 1. So you can see that in this table here. With a NOT gate, which is the third one, it is inverting the signal. So whatever goes in, the opposite will come out. So if I put a 0 in, a 1 will come out. Your last questions here are, explain how a comparator circuit works and name an input sensor that can be used to detect changes in temperature levels. Have a look, answer your question, pause, and check your answer. So here's an example of a comparator circuit. You can see the comparator with the triangle IC1. They compare two input voltage signals and decide which one is greater. The result can be indicated using LEDs, lamps, and buzzers. In this example, and there is a link here which you can type in, and it's a really good revision website where you can see the outcome and play with the circuit. In the example below, you can see the LDR is used with a resistor to adjust the input voltage. The simulation on this website, if you can go to this and play around with it, you can see what happens as the voltage increases or decreases and which LED lights up and how that is triggered. So I do recommend going to this website and typing out that link. Then we name an input sensor that can be used to detect changes in temperature levels. For this, we would use a thermistor, and the symbol for this is shown here. A thermistor is a variable type of resistor. They can change the temperature level that's detected into a resistance. If the temperature goes up, then the resistance will decrease. Think about it as we, in a previous question, talked about how light sensors work. It's a similar concept. But you might see a thermistor used in fish tanks or greenhouses, and really industries that have to have specific temperatures, such as cooling in a nuclear power plant. So they're there to ensure that the temperature is kept at a consistent rate.